Okay, so welcome back everyone. In this set of videos, we'll be talking about some review of proof techniques that you might have seen in your discrete structure or discrete math class that I just want to remind you of because you'll be seeing some similar proofs throughout a potential theoretical computer science course. Um, so the first proof technique that I'm going to talk about, and I think I'm going to split these into multiple videos. In this video, we'll be talking about the equality of sets proof technique. So, to prove that for two sets, A and B, you have that A is equal to B. One quote unquote straightforward way of doing this is by double inclusion. So, this proof technique of double inclusion just consists of first showing that A is a subset of B, and then showing that B is a subset of A, right? And how do you show inclusion, right? So this is by double inclusion, but how do you even show just one inclusion? To show that, say, A is a subset of B, what you must do is pick an arbitrary element A, little a in A. So what does it mean that you're picking an arbitrary element, little a and A? It means that you're picking an element in the set A for which you only know that it belongs to A. That's the only thing you know about this element, is that it belongs to the set A. And then you have to show through a sequence of um, logical reasonings that this element, the same element that you picked arbitrarily, is also in B, right? Is also in B. And so what that'll imply, right? So that'll imply that because A was selected arbitrarily, right? So because A was any A, right? Because A was selected arbitrarily, this will imply that, in fact, for any little a in the set A, this little a will also belong to B. And this is the definition of a subset, right? So this implies that the set A is a subset of the set B. And to show that the set A is equal to the set B, you must do this in sort of both directions, right? So it's kind of like an if and only if proof, except that now it's just double inclusion, or it's two sides of the inclusion. So you have to show that A is a subset of B, right? So in other words, you're showing that A is within B, and then you're showing that, then you must show that B is a subset of A, so B is within A. And by showing these two things, it must imply that actually A and B are the same, right? Are one and the same. Okay? So A subset B and B subset A implies that these two sets are identical. Okay, so let's look at an example. Here, as promised in a few videos ago, we're going to prove one of De Morgan's laws for sets, right? So we want to prove that the complement of A intersect B is equal to the union of the complements. Okay, so how do I prove this? So I'm going to prove this, so proof. I'm going to do this by double inclusion. Inclusion. All right, there's an extra S there. So the first way I'm going to do this, so the first direction, if you want, is I'm going to show that the complement of A intersect B is a subset of the union of the complements. Right? Okay, so how do I do this? Remember, I just pick an arbitrary X in A intersect B complement, right? And now I try to argue that this implies that X is also in the set on the right. So X belonging to the complement of A intersect B means that X, so what does this imply? This implies that X does not belong to, so this implies that X is not in A intersect B, right? So if X is not in A intersect B, right? So if you think of this as just a set, right? So if X is not in here, if is not in the intersection, then that must mean either that X was not in A or X was not in B, right? So this implies that X is not in A or X is not in B, right? Because for an element not to be in the intersection, then it means that by definition of what you do in an intersection, it can't be in either A or B or both, right? So this is not an exclusive or, right? So not an exclusive or, right? So either X is not in A or X is not in B, or also X is not in both. Then that would that's how you would get to the conclusion that X is not in A intersect B, right? Okay, so what does this mean? This means that X is not in A or X is not in B, right? But what does this mean, right? This means that by definition of the complement, this means that if X is not in A, it means that X is an A complement, or X is in B complement, right? So this is just by definition of the complement, right? Okay, so X is an A complement or X is in B complement. That implies, by definition of the union, that X is in A complement union B complement, right? Because remember the definition of a union of sets. So if I take, I'm not going to use the same letters. If I take X union Y, then X union Y is the set of elements X such that X is in X or X is in Y, right? And so that means that I've achieved my goal of saying that I picked an arbitrary X in the complement of A intersect B. Then I said that, okay, that means that X is not in here, right? It's not in that part of the intersection. So if it's not part of the intersection, right, then it means that it's not in here, or it's not in here, or it's not in either of these two things, right? So maybe X is here, right? Because so I think the hardest part of this proof is understanding from this step to this step, okay? And implicitly, what I'm just saying is I'm saying this is my universe, right? This is my universe. And I'm saying that, let's see, I'm saying that X, let's do this very clearly. Okay, I'm saying that X is not in A intersect B, right? So then I have three cases then, right? If it's not in if it's not in the intersection, then that must either mean that it's because it wasn't in here, so it only means that it wasn't in A, or it wasn't in B, or it wasn't in both. Okay, but these three cases together are equivalent to just saying X is not in A or X is not in B. So I think this part of the proof is perhaps the trickiest. This sequence or this step, this reasoning step, but it just requires this implicit reasoning that you're sort of exhausting all cases of where X can't be. Okay? And then from this step to this step, that's just, rewriting what it means for something not to be in a set with set notation. Then this is just by definition of the complement, right? So this step here is by definition of the complement. And finally, this step is just by definition of the union. Okay. All right. So that was one direction of the inclusion. The other direction of the inclusion is now I need to show that A complement union B complement is a subset of A intersect B complement. Okay, so I'm going to again do the same thing. I'm going to reduce my font style, I think, so I have more space. So I'm going to pick X in A complement union B complement. So what does that imply? That means that X is in A complement or X is in B complement, right? So X isn't in A or it's not in B. What does that imply? So this implies that X is not in A or X is not in B. Okay, so I know that either of these two things are true, or both, right? So either X is not in A, or X is not in B, or perhaps both, right? This isn't an exclusive or. So what this means, what I know for sure then, right? This guarantees that X cannot be in both A and B, right? It guarantees that X cannot be in both A and B because I know that it's at least not in A or B, right? So this implies that X is not in A and so it implies that X is not in A and B at the same time. So it implies that X is not in A intersect B, right? And so, because I know that if I'm not in A or in B, then I certainly can't be in both, right? I can't be in the intersection here, right? If I know that I'm not here or here, right? So remember, this is like an or, right? So either of the things can be true for the clause to be true. Then it certainly means that I can't be in here, right? If I'm not in here or in here, it means that I can't be in here. So this implies that X cannot be in the intersection. So this implies that by definition of the complement that X is in the complement of the intersection. So this is by definition of the complement. So the real crux of this proof is just understanding what it means. Like the crux of the proof is understanding the implications of a set membership. So it's understanding this from this step to this step and from this step to this step, right? Okay, so by the last two sort of sub-proofs, I've shown that A intersect B complement is a subset of A complement union B complement, and that A complement union B complement is a subset of A intersect B complement. So because I've shown both, right? Because I've shown both subset inclusions, then I've shown that these two sets are in fact one and the same. And so that proves, so I can put my little square here, that proves that the two sets are equal. Okay, and that's a way that you can prove um, that two sets are equal. So this is an example of the double inclusion proof technique for proving set equalities. So in the next video, we'll be talking about another very famous proof technique, the proof by contradiction.